In this video, we focus on bearings, with particular attention to the group of rolling bearings. In almost all machines and technical systems, components such as shafts, axles, or bolts must be able to move relative to one another. One example is a shaft in a gearbox, where gears are mounted and rotate together with the shafts. Bearings play a central role in such cases. They hold rotating components precisely in position, transfer the resulting forces in a controlled manner to the housing or adjacent components, and at the same time enable a defined movement, such as a rotation, with minimal friction. In engineering, the possible movements of a body are referred to as degrees of freedom. A body can fundamentally move translationally in three spatial directions x, y, and z, that is, meaning essentially to the right and left, forward and backward, as well as up and down. Additionally, a body can rotate about these three spatial axes, that is, about the y-axis, the z-axis, and the x-axis. In total, there are 6 degrees of freedom. The function of bearings is to selectively restrict certain degrees of freedom so that only the movements necessary for the function are allowed. A gear shaft, for example, is supported in such a way that it is fixed in space and can perform only a rotational movement around its longitudinal axis. It therefore has only one rotational degree of freedom. So note, bearings have the task of selectively limiting degrees of freedom in order to reliably enable desired types of movement. Special types of bearings designed for movement with minimal friction are called rolling bearings and plain bearings. In a plain bearing, the moving component slides directly on the bearing surface inside the housing. A common everyday example of a plain bearing is a door hinge. There, a pin slides within a bushing, allowing the door to rotate. The characteristic feature of a plain bearing is the sliding friction that occurs between the contact surfaces. To minimize this friction, lubricants such as oil or grease are often used. Plain bearings have a simple design but are sensitive to dirt and often require more maintenance than other types of bearings. In contrast, rolling bearings operate with rolling elements that are positioned between an inner ring and an outer ring. These rolling elements can be small balls, rollers, needles, cones, or barrels. During operation, these elements roll between the rings, largely replacing sliding friction with rolling friction. Since rolling friction is physically much lower than sliding friction, rolling bearings are characterized by low energy loss. They also often require less maintenance. In this video, we will focus primarily on the group of rolling bearings. Another important criterion for classifying rolling bearings is the direction of the forces they can support. So-called radial bearings are designed to absorb forces that act perpendicular or radial to the axis of rotation of the shaft. Such forces can result from the weight of a rotating component or from lateral loads during operation, such as the side forces acting on the flanks of gears. Axial bearings or thrust bearings, on the other hand, can support forces that act axially along the axis of rotation. This type of bearing is used, for example, in spindles or screw drives, where components are subjected to loads in the longitudinal direction. In many technical applications, both radial and axial forces act simultaneously. Therefore, there are also combined types of bearings that can support both types of loads. However, they often have limitations regarding the maximum load capacity in one of the two directions. We will take a closer look at all of these types of bearings in this video. Let us now take a closer look at the structure of a rolling bearing using the example of a ball bearing. As the name suggests, balls are used as rolling elements in this type of bearing. To prevent the rolling elements from touching or jamming each other, they are guided and spaced by a so-called cage. The cage ensures an even distribution of the rolling elements and thus a smooth and consistent operation of the bearing. Depending on the application, the cage is made of pressed sheet steel, aluminum alloys, or glass fiber reinforced plastic. In particularly large or heavily loaded bearings, solid cages made of brass are also used. Only very low sliding friction occurs between the cage and the rolling elements. The rolling elements move between an inner ring and an outer ring, also called inner and outer race. One of these rings is connected to the rotating component, the other to the stationary housing. In the illustrated gearbox shaft, the inner ring is connected to the shaft and the outer ring to the gearbox housing. On the inner surfaces of these rings are the raceways on which the rolling elements roll. To withstand high forces and wear, these raceways are hardened, usually to a Rockwell hardness of about 62 HRC. The bearing rings are typically made from wear-resistant chromium alloyed tool steels. Rolling bearings can also be equipped with seals to retain the lubricant inside the bearing and to prevent contamination from external dirt. Let us now take a closer look at the different rolling elements and rolling bearings used in practice, as well as their advantages and disadvantages. If the rolling elements are balls, the bearing is called a ball bearing. Deep groove ball bearings are the simplest design, highly versatile, and therefore the most widely used. In this design, the balls roll in a semicircular groove in the inner ring and outer ring. These bearings are especially suitable for supporting radial forces, which is why they are also referred to as radial deep groove ball bearings. Due to the point contact between the balls and the raceways in ball bearings, relatively low friction losses occur, enabling high rotational speeds. In technical drawings, ball bearings are usually shown in full section, with the rolling elements not cut through. Since a rolling bearing is a pre-assembled integrated unit, the inner and outer rings are given the same hatching to indicate their association. For reasons of clarity, the cage is usually not shown. Deep groove ball bearings are available both in open designs and with shields. These non-contact metal shields protect the bearing from coarse dirt and splashing water, but offer only limited protection against moisture or fine particles. Their advantage lies in very low friction. The shields are firmly mounted in the outer ring without touching the inner ring. As a result, the maximum permissible rotational speed of the bearing remains unaffected. For improved sealing, special sealing shields made of NBR are used. They have a significantly smaller gap to the inner ring, enabling a more effective sealing function, especially against moisture and fine contaminants. However, contact may occur. Therefore, these seals are classified as low-friction contact seals. An even higher sealing effect is achieved by seals with a sealing lip that directly contacts the inner ring. These contact seals provide near-complete protection of the bearing interior but generate additional friction. As a result, the maximum rotational speeds are significantly lower than with non-contact seals. In the shown designs, the rolling elements are arranged in a single row only. This is why they are also called single-row ball bearings. If the load capacity of a single-row bearing is not sufficient, double-row designs are used. Double-row deep groove ball bearings contain 2 rows of balls within a common inner and outer ring. Compared to single-row bearings with the same inner and outer diameter, they have only a relatively small additional width but offer significantly higher load capacity. As mentioned earlier, radial deep groove ball bearings are especially designed for radial forces, but they are also suitable to a limited extent for axial forces. When higher axial forces are expected, so-called angular contact ball bearings are used. Such single-row bearings have inclined raceways that allow them to support both radial and axial loads. In the single-row design, the installation direction of the angular contact ball bearings must be considered because the raceways are inclined in only one direction and can therefore be loaded axially to the maximum only from one side. The bearing must be installed in the shown situation so that the inclined raceway of the inner ring faces the shaft shoulder. The raceway of the outer ring must be aligned accordingly with the housing shoulder. In this way, the shaft can transmit a force to the left onto the inner ring, which transfers it via the rolling elements to the outer ring. The load is then directed from the housing shoulder into the housing. If the bearing were installed rotated by 180 degrees, there would be a risk that the inner ring could be pushed out of the bearing under high load. The ability of an angular contact ball bearing to support axial forces increases with the contact angle. This so-called pressure angle describes the direction in which forces are transmitted through the ball from one raceway to the other. It is determined by the line passing through the 2 contact points between the ball and the raceways and its angle relative to the radial plane of the bearing. To support axial forces equally well in both directions, 2 angular contact ball bearings can in principle be arranged in a mirrored configuration. The shaft and housing must be designed so that the shaft can transmit forces to the respective inner rings in both directions, and the housing is capable of receiving and transferring these forces through the outer rings. Such an arrangement is also available as a pre-assembled bearing called a double-row angular contact ball bearing. The raceways are designed so that the pressure lines intersect outside the bearing, forming what is known as a back-to-back arrangement. In this arrangement, the intersection points of the pressure lines lie outside the bearing and form the load application points, allowing the support points to be virtually shifted outward. In the face-to-face arrangement, the raised raceway of the inner ring faces the inside of the bearing, and the raised raceway of the outer ring faces the outside. The intersection points of the pressure lines are closer together in this design. This arrangement is more prone to tilting due to the closer load application points, but can better compensate for misalignment. As a result, the stiffness of the bearing arrangement is reduced, leading to less precise guidance of the shaft. In contrast, the back-to-back arrangement provides significantly higher stiffness due to the virtual widening of the support points and is less prone to tilting. For this reason, the back-to-back arrangement is preferred for double-row angular contact ball bearings. Let us briefly examine the assembly of such a double-row angular contact ball bearing. First, the balls are dropped into the raceway of the outer ring. Then the inner ring is slid in through the resulting assembly gap. The balls are then distributed onto the two raceways and secured with the cage. Due to this assembly method, the maximum number of balls in the bearing is limited. In contrast, a split inner ring allows for a significantly larger number of balls. First, all the balls are inserted together with the cage into the outer ring. Then, the two halves of the inner ring are slid in from both sides and joined together. This eliminates the assembly gap, allowing the bearing to be equipped with a higher number of balls, which increases its load capacity. Additionally, the guide tracks at the end faces of the inner ring can be reinforced or made taller since the inner ring does not need to be slid over the balls in this design. This allows for larger contact angles to be achieved, for example 45 degrees, which significantly increases the axial load capacity. For easy maintenance, lubrication holes and a continuous lubrication groove can additionally be provided in the outer ring to facilitate relubrication. The continuous groove has the advantage that the lubrication hole in the bearing does not have to align precisely with a lubrication hole in the housing. Furthermore, multiple lubrication points can be implemented on the housing, through which the grease is injected. The grease then distributes evenly via the lubrication groove to the lubrication holes, ensuring reliable delivery to the rolling elements. In addition to double-row angular contact ball bearings with a split inner ring, there are also versions with a split outer ring. Due to their design, these can only be realized in the face-to-face arrangement. Such bearings are preferably used where the shaft is difficult to access or permanently installed, for example, in combination with split housings. A special design of single-row angular contact ball bearings that, similar to double-row types, can absorb axial forces in both directions is the so-called four-point bearing. The raceways are designed so that each ball makes contact with the raceways at 4 points simultaneously, which gives the bearing its name. In contrast to other bearing types, their ability to absorb radial forces is, however, very limited. A design advantage of this bearing is that the outer ring together with the ball cage can be mounted separately from the split inner ring. Since the individual bearing components are not firmly connected, this type of bearing is also referred to as a non-self-retaining bearing. This particularly facilitates assembly in difficult installation conditions or complex housing designs. Since four-point bearings are primarily designed to accommodate axial forces, higher radial loads must be absorbed by additional bearings, for example, through combination with a cylindrical roller bearing, which we will discuss in more detail later. Single-row ball bearings can compensate small misalignments of the shaft because they are less rigid. Double-row ball bearings cannot do this well because their rolling elements would be damaged. In certain applications, a deliberate shaft misalignment is required alongside high load capacity, or misalignments occur during operation due to thermal expansion, housing settling, or shaft bending. For such cases, so-called self-aligning ball bearings are suitable because they are designed to reliably compensate for misalignments. They have 2 rows of balls and a spherical raceway in the outer ring. This design allows them to compensate misalignments between shaft and housing of up to about 3 degrees. Therefore, they are often used with long shafts or in assembly situations with limited alignment options. Self-aligning ball bearings are available as open bearings or in sealed versions. The point contact area of balls as rolling elements has the advantage of producing low friction. This allows for high rotational speeds without significant heating. At the same time, however, the point contact results in high surface pressure, which leads to greater stress on the raceways. Therefore, in applications where higher radial load capacity is required but lower rotational speeds are sufficient, cylindrical rollers are used as rolling elements instead of balls. Such rolling bearings are called cylindrical roller bearings. However, compared to ball bearings, roller bearings are more sensitive to misalignment and can only absorb limited or no axial loads. For the cylindrical roller bearing variant NU, only the outer ring has flanges between which the rollers are guided. The inner ring, however, has no flanges and can move axially. In the variant N, the situation is reversed. Only the inner ring has flanges, while the outer ring has none. Both variants, N and NU, cannot absorb axial forces. However, assembly is much easier because the shaft or housing only needs to be slid through the other bearing half, once one half is already mounted. Another design of cylindrical roller bearings is the NJ variant. In this type, the outer ring has flanges on both sides, while the inner ring has a fixed flange on only one side. This means the bearing is axially guided and fixed in one direction, but not in the opposite direction. However, the flange on the inner ring serves only for guidance and is not designed to carry significant axial loads. Another bearing design is the NUP cylindrical roller bearing, which provides axial guidance in both directions. The inner ring has a fixed flange on one side. On the opposite side, a separate loose flange ring is supplied. This flange ring is pushed onto the inner ring during assembly and acts as a second flange. As a result, the bearing is axially fixed in both directions. The combination of a fixed flange and a loose flange ring allows for easy installation, especially in cases where the bearing seat is difficult to access or when the shaft is inserted through the bearing first. A special type of roller bearing is the so-called needle bearing. The rolling elements are significantly slimmer and longer than in cylindrical roller bearings. Due to the many small rollers, needle bearings have a very high radial load capacity while being extremely compact. They are mainly used in applications with limited installation space, such as in gearboxes, joints, or small auxiliary units. However, they are not suitable for axial loads and usually require very good lubrication. Needle bearings are available in various versions. The NA design has two flanges on the outer ring. These provide axial guidance for the rolling elements. The inner ring has no flanges. For maintenance, the outer ring features a circumferential groove with a lubrication hole. This allows the bearing to be relubricated even while installed. The RNA design belongs to the type without an inner ring. It therefore consists only of an outer ring with a needle roller cage and is especially suitable for space-saving designs. A hardened and ground shaft is required, as it serves directly as the raceway. Two fixed flanges on the outer ring provide axial guidance for the needles. A lubrication hole is also present on the outer ring. In addition to these two designs, there are many others which we will not discuss in detail here. A special variant of the needle roller bearing consists solely of the needle roller cage without inner or outer ring. In this case, both the surface of the bore and the shaft itself serve directly as the running surface for the needle rollers. Such needle roller bearings are simply called needle roller assemblies. The advantage of needle roller assemblies lies in their extremely low radial height. If the housing bore cannot be used directly as a raceway, special needle roller bearings with a thin-walled outer ring, called drawn cup needle roller bearings, are used. This outer ring serves as the raceway and is press-fitted into the housing bore. In many applications, this allows for omitting axial securing elements such as retaining rings or snap rings. Needle roller bearings are available not only in single row but also in double row designs, allowing for higher load capacity. Misalignment errors usually cannot be compensated by conventional needle roller bearings. However, special designs such as self-aligning needle roller bearings provide a solution. They feature a spherical outer ring and are installed in a correspondingly shaped housing seat. This design allows them to compensate for angular errors and misalignments of up to about 3 degrees, which can occur, for example, due to shaft bending. Such alignment needle roller bearings are available both without and with inner ring. As already explained, cylindrical roller bearings or needle bearings can only take up axial forces to a limited extent or not at all depending on their design. To simultaneously absorb large axial forces, tapered rollers are used instead of cylindrical rollers. These are called tapered roller bearings. They are usually non-self-retaining bearings, as the outer ring can be removed and mounted separately from the inner ring. Due to the conical shape of the rolling elements, tapered roller bearings can handle both very high radial forces and high axial forces. The imaginary extension of all tapered surfaces intersects at a common point on the bearing axis. This allows the rolling elements to roll on each other without sliding, enabling low-friction operation. The ability to absorb axial forces increases with the so-called contact angle alpha, which is usually between 10 degrees and 30 degrees. Due to their tapered geometry and line contact, tapered roller bearings are significantly more sensitive to excessive or insufficient clearance than angular contact ball bearings with their spherical rolling elements. Therefore, tapered roller bearings require very precise adjustment of axial clearance, as otherwise excessive friction, strong heating, and increased wear can occur. Matched tapered roller bearings are factory-matched bearing pairs, used together as a set, similar to the face-to-face or back-to-back arrangement in angular contact ball bearings. In the face-to-face arrangement, the load lines run toward the bearing axis and intersect inside the bearing. This design allows for compensation of minor misalignments, and is especially suitable for shaft side expansions or slight shaft deflections. The back-to-back arrangement, on the other hand, has load lines running outward that intersect outside the bearing. This results in high stiffness and good resistance to tilting moments, making it preferred for applications with high demands on bearing guidance. Since the bearings are delivered from the factory with defined clearance or preload, complex adjustment during installation is not required. Matched tapered roller bearings are especially used in axle bearings, gearboxes, and machine tools, where axial forces must be reliably absorbed in both directions. Tapered roller bearings can handle very high radial and axial forces, but tolerate almost no misalignment or shaft deflection. This is especially true for cylindrical roller bearings. To combine the high load capacity of the line contact of the rolling elements with the ability to compensate for angular errors or shaft bending, spherical roller bearings with barrel-shaped rolling elements are used. These spherical roller bearings, also called self-aligning roller bearings, have a spherical outer ring raceway that combines high radial load capacity with the ability to compensate for misalignment up to 3 degrees. This makes them especially suitable for applications with dynamic loads and possible misalignment, such as heavy vibration-prone or oscillating machines or systems with elastically supported shafts. Besides the single-row version, spherical roller bearings are also available in a double-row design to handle even higher loads. Sealed bearings are also possible. To prevent the rollers from contacting the seals during misalignment, sealed spherical roller bearings are usually designed slightly wider than comparable open versions. In addition to versions with cylindrical bore, spherical roller bearings are also available with tapered bore. These allow for easy, play-free mounting on tapered shafts. By pressing them on, the bearing clearance can be precisely adjusted. With the help of adapter sleeves, such bearings can also be mounted on cylindrical shafts. This variant is especially advantageous for frequent bearing replacements or when complex shaft machining should be avoided. First, the slotted adapter sleeve with a mounted bearing is pushed onto the shaft. Then a tab washer is fitted and a slotted lock nut is screwed onto the thread of the adapter sleeve. The adapter sleeve acts like a tapered mandrel that pulls the bearing onto the shaft. By pushing the sleeve forward, the inner ring expands slightly, allowing the bearing clearance, which means the gap between rolling elements and the outer ring raceway to be precisely adjusted. The bearings considered so far are mainly designed to support forces in the radial direction and are therefore called radial bearings. In addition, there are also bearings specifically designed to accommodate axial forces. These are generally referred to as thrust bearings. Depending on the rolling element used, different types are distinguished, each with its own specific designation. Single-direction thrust ball bearings are designed to absorb axial forces in one direction and usually consist of a cage with a ball set and 2 raceways. They are non-self-retaining bearings, so individual bearing components can be easily replaced, which simplifies assembly. However, since there is no fixation in the radial direction, these bearings are not suitable for absorbing radial forces. The 2 raceways of a thrust ball bearing differ in bore diameter. The raceway that fits onto the shaft, called the shaft washer, has a smaller bore than the opposing housing washer. This design ensures that the shaft only contacts the shaft washer. As a result, the axial force is fully transmitted from the shaft through the rolling elements to the housing raceway. Thrust bearings usually cannot compensate for misalignment between shaft and housing. In certain applications, where a shaft bends for example, or where misalignments due to manufacturing tolerances are expected, slight shaft deflections must be compensated. Therefore, there are thrust ball bearings with spherical housing washer, combined with a matching spherical seat washer. This special design allows the housing washer to align within the bearing housing, and enables compensation of misalignments up to 3 degrees. The thrust ball bearings presented so far can absorb axial forces only in one direction each. For applications with axial loads in both directions, double-row variants are also available, where a set of balls acts on each side. The intermediate washer is connected to the shaft and functions as the shaft washer. It has a correspondingly smaller inner diameter than the 2 outer housing washers. These double-direction thrust ball bearings are also available with spherically shaped housing washers and matching seat washers to compensate for minor misalignments between shaft and housing. The axial load capacity of ball bearings is limited due to the point contact between the spherical rolling elements and the raceways, which leads to high surface pressures. For heavily loaded applications, cylindrical rollers are therefore used as rolling elements, guided between two washers. Cylindrical roller bearings are available not only as single-direction bearings but also as double-direction bearings, which can absorb axial forces in both directions accordingly. Thrust cylindrical roller bearings can carry significantly higher axial loads than thrust ball bearings, but they are more sensitive to misalignment and generally achieve lower speeds compared to thrust ball bearings. These separable cylindrical roller bearings, due to their non-self-retaining design, also cannot absorb radial forces. Besides these complete thrust cylindrical roller bearings consisting of rolling elements and multiple washers, there are also simpler and more space-saving versions called thrust cylindrical roller assemblies. Thrust cylindrical roller assemblies consist only of a cage with fitted cylindrical rollers and do not include shaft or housing washers. They are suitable for applications where no separate washers are required because the adjacent components already serve as raceways. This allows for very flat and compact bearing arrangements. However, the roller assemblies require very precisely machined counter surfaces in the housing or on the shaft shoulder. If the raceways cannot be properly ground and hardened, complete thrust cylindrical roller bearings must be used. However, to further reduce the axial installation height, much smaller rollers can be used instead of cylindrical rollers. In this case, they are referred to as thrust needle roller bearings. These bearings are also available in a version without raceway washers if the existing surfaces in the housing or on the shaft shoulder can be used directly as raceways. These are then called thrust needle roller assemblies. This bearing design is characterized by an especially low overall height and is often used in combination with radial bearings. Thrust needle roller bearings are also available with a so-called centering flange. This centering flange ensures precise alignment of the washer in the housing or on the shaft, thereby simplifying assembly. At the same time, it prevents the washer from shifting during operation. When the rolling elements are in direct contact with the shaft shoulder, this surface must be ground and hardened. This bearing design offers a compact, easy to assemble, and cost-effective solution. To support a simultaneous radial load, this thrust needle bearing can be combined with a radial drawn cup needle bearing. In the case of direct mounting, the shaft surface must also be ground and hardened. Alternatively, a radial needle bearing with an inner ring can be used. In special bearing designs, axial and radial bearings are also combined and supplied as ready-to-install bearing sets, for example needle axial ball bearings. These enable the absorption of very high axial and radial forces while maintaining a compact design. Such combined needle roller bearings are available both with cages and in a so-called full complement thrust ball design, where the balls lie directly against each other without a cage. Due to the large number of balls, this design can absorb particularly high axial forces. However, because of the direct contact between the balls, only comparatively low speeds are possible. Another type of bearing is the spherical roller thrust bearing, which can absorb high axial forces in one direction and also withstand radial forces. Its characteristic self-aligning function is achieved by a spherical raceway in the housing, allowing the bearing to compensate for angular misalignment between shaft and housing. It consists of rollers guided in an inclined cage. It is typically used in applications with high axial loads, such as heavy-duty presses, ship drives, or conveyor systems.